Yeah, thanks for that intro. That puts us on the right path now. So, yeah, as a reminder, keep asking questions. Um, we'll be talking now, but there's other people who will be answering. Um, let's see. I have Yeah, so what do we do now? Now we've got an example where we go through exercises. Well, not really exercises, it's a demo. So we have this model problem where we analyze a bunch of public domain books from Project Gutenberg. We'll go through all the steps that someone might go through. So we will go through downloading data, copying it to the cluster, getting our project set up, running things in different ways. Um, um, yeah,
And this example that we are going to be giving, it's not like I wouldn't recommend trying to follow it, like try to type along it. It's better to watch it and like try to see what is the usual like workflow that you might do when you're running stuff in the cluster. So what we're trying to like show is like a simple example that okay, this is how a typical workflow might go through. Of course, the case here is very small, but we'll try to show like a typical thing that people do when they do in the cluster. And in the afternoon, we have a lot more time to actually replicate the same thing if you want to try it out yourself.
yeah. So normally we'd have this course over several days, over 3 days, where the first day is a broad intro and the second 2 days for 4 hours per day are doing exercises together. And now we're trying to do a similar amount of stuff in an hour and a half. So it really is an impossible situation we've got here that we're trying to do. But that's okay. Um, yes. Um, so what's our example? So if you look down here in the notes, I've added a link to the series of things we'll be doing, but don't, this isn't something you can really follow because we'll be saying a lot of things that aren't in here. But this is sort of like the um, big picture thing. So our general plan is we do the demos now, and then in the afternoon, there's time you can come and work on it yourself by reading the material and trying to follow along in a more structured manner. Um, I'm trying to give a link to the tutorials here. Okay, I'm adding it to the notes.
I think it's already is. Mm.
So,
Oh, it does.
okay,
Yeah.
yeah. So what is the example we want to do then? So our previous example was calculating pi, where basically we would, it's like a stochastic method of calculating pi. You pick a random point within a square and see does the point fall in a circle, and if you do this enough, you can um, rearrange the fraction to be pi. But this is a more data example. So in this example, what we will do, we take um, Project Gutenberg is a project which takes public domain books and makes them available. So we found a data set of several thousands or tens of thousands of books of fiction books from Project Gutenberg. And all of these books are taken and we compute ngrams in them. So an ngram is basically like a sequence of words or characters that you see together. So for example, th are often next to each other, or the words the is right before some other word, and so on. So we have some simple code which can analyze all of these books and then compute the distribution of all ngrams within them. And yeah, so if you want to, you can take this and use it to predict the next words that might come up in a sequence, but we probably won't go that far. So is this an appropriate problem for a cluster? What would you say, Simo?
Yeah, so I think this would be like, of course, if the problem becomes bigger, like if we are dealing with the whole Gutenberg dataset or something, like suddenly we have a huge amount of books, it immediately can go from like something that is feasible to do on your laptop to something that is only possible to do on a cluster. So this case is a good example of a case where um, you might want to like split up the job among like books. Like you maybe want to analyze
Yeah,
some books with one computer and some other books with another computer so that you can do it faster. Like you can
yeah.
easily split it up among the data. So it's
Mhm.
it's very easy to get it rolling in the cluster. So it's very like a data centric situation, and this can happen quite a lot. That often we are doing the same thing over and over again, and in this case, we are analyzing different books, but we could run different parameters and stuff like that. And these kind of cases are very good for the cluster because your laptop it doesn't have to do all of those calculations
Yeah,
itself.
yeah. So there was this question earlier on how do you know if a problem will be well suited for a cluster? And in this case, like Simo said, since the data can be divided and each book can be analyzed separately, then yes, this will probably be distributed pretty well among the cluster. We don't have any communication we need here. So we're already thinking that way. So of course, the data is a little bit too small to need the cluster, but well, it's an example, so that's okay. Simo, should I switch to your screen?
Yeah, sure.
Okay, let's see. Yeah, so you see here the series of exercises we'll do. Um, we'll roughly be typing the things from here, although we won't be doing some of the earlier cluster from the command line exercises. Um,
Yeah, maybe should we start
yeah,
with getting the data into Triton? Like the first thing
yes,
usually what happens is that
okay,
like you have something you want to do and you need to get it to
yeah,
the cluster. So in this case,
yeah.
uh, what I would now do is
So,
download the data to my own laptop.
yeah. So quite often what we would have people do is try to transfer the data directly to the cluster and not through the and not downloading to your computer and then uploading to the cluster if the data is big. But we want to demonstrate how you would transfer data to a cluster because that's something that's really um, that's a common thing. It's something we haven't usually demonstrated. So, Simo, you've downloaded a zip file. Yes, I see the zip
Yes.
file here. Okay,
So
so
there's multiple ways you can do the transfer, but this time I will be using the on-demand that Enrico brought up previously. So yeah,
yeah,
Richard, if you explain
yeah.
what I'm doing.
Okay, so OnDemand is a web interface for the cluster. So you can go there with the web browser, and then you can, so Simo's already logged in here. You can browse different storage locations. You can get the shell access this way. You can run Jupyter, or you can even get a graphical desktop here. So
So
this is nice because it's easy to use and can be used from any web browser. It's not the most powerful thing, but sometimes convenience is more important. And for this transferring data, that's the case.
And when we are talking about transferring data, where are we actually transferring the data?
Yeah, that's a good question. So before we transfer the data, we need to stop and think, where do we want to put it? So it often happens that people begin working, they throw data somewhere, and then it becomes a giant mess, and that's not good. So this is a project. Will it be a personal project or a group project?
Well, in this case, I would say it's a personal project,
Mhm.
let's say.
So we can put it in your personal Scratch directory, your personal work directory. So even for personal project, we would generally recommend that people create a shared directory for their group so you can share later when it comes up. But for something small, we can start here. So I see Simo can browse to the work directory. It also
And
shows the
because I
path
have
on the cluster.
Yeah,
Oh,
and because I
yeah.
have, of course, a lot of projects, I have a lot of directories already here. So I'm going to jump into like a subdirectory here, so that we can keep it a bit clearer. For you, your case, you might have your work directory might be completely empty, so you don't have to necessarily go into a subfolder, but it's usually a good idea to have some sort of like mental separation between the projects and folder structure to represent that separation in the work directory so that you can find whatever you have stored there.
Yeah. Uh, did you talk about the path here? So we see it's /scratch/work/ Simo's user's name teaching winter kickstart.
Yeah, so the main
Yeah.
things here is that the Scratch directory, yeah, it doesn't mean that it's going to be scratched like thrown away immediately. It means that it comes from the fast network file system, the Lustre file system that the cluster has. So Scratch is the place where that file system resides in the cluster. So whenever you go to Triton, to the login node or to the on-demand or to the compute nodes, the /scratch is the fast file system. There is also a home file system, which is mainly for storing like authentication secrets and that sort of stuff. But it's not good for computing because it's small and it's not fast. And this is large and it is fast.
Yeah.
And underneath there, we have lots of project folders. Like if you have a research group and you want to collaborate among the research group, we can create you a project folder to there. It's easy to get one, and you should get one if you want to do like a collaborative project. Otherwise, you can put stuff into your own work directory, which is under Scratch work and your username.
Yeah. Yes. So okay, should we upload the data now?
Yeah, but
So
I'll create a new
luckily from
directory called data so that
uh
we can keep it like clear, and let's
yeah,
upload it into the
good
data
idea.
folder.
Okay. And we can do it from the web here, which is nice.
Let's see
Is
if the
this how
drag
you
and
would
drop
normally
works.
transfer? Oh, nice. Yeah, cool.
Yeah,
So is this how you would normally transfer data to the cluster yourself?
well, I would probably use command line tools like rsync and stuff like that because, well, I'm
Okay.
familiar with those. But
Yeah.
in the case of small files or individual files, it's very
Yeah.
easy to transfer. But if you're transferring lots of files and you want to verify that they are transferred correctly, you might use
Yeah.
other tools as well. Or you might mount the
Yeah.
file system into your
Mhm.
laptop so that you can straight up copy uh,
Yeah.
files from your laptop there.
Yeah. Okay. So now we've got our data on the cluster. So we also need some code there. And the code's
Yes.
all already made, and it's in a Git repository called HPC examples. So this repository has a bunch of small sample programs useful for stuff. And so again, we're not going to talk about the way version control works in details, but since we have it there, we can run a command git clone and then copy it all onto the cluster.
Yeah, so to
So
get to the place where we previously were, like in order to now run that command, I need to first connect to Triton. So I will use an SSH client. You could use from the on-demand, you could open this in a terminal in the web browser as well. But because I'm more used to running stuff through the SSH, so I'm taking a remote connection to the cluster and taking an SSH. So now I'm the name changes here. So now I'm in the login node of the cluster, and then I'm going to go to the folder where I previously put data.
Yeah, and it's really important to be able to match up the place you put data from the different interfaces. If you upload data by OnDemand but don't know where it is in the command line, then you've got a bit of a problem. But okay, so here
So
we
you can
are,
see that
and
I used the command called cd to go to the folder, like change directory, and then I'm using command called list ls to list the files, so I can notice that the files are now there. And
yes,
now
okay, yeah, so we verified it's there, and git clone.
okay, so now we got the code. Richard, what should I do next?
So let's see, let's look at our thing. We've cloned it, and you've listed it, yes. So I guess first let's verify that the code works at all. So we are going to run Python on the relevant code, which is ngrams. So ngrams count.py. And now we're at the point we have to know how the code even works. So this is the code that we wrote ourselves, so you know. If you wrote your own code, you would know how it works. And for other code, well, you need to read about it and see. Okay,
Usually
so
codes
yeah,
like this have these kind of like documentation inside of it. So there's few conventions such as dash dash help will usually provide output. So Richard has written a nice
yeah,
help output here that will describe how the code works. This applies to other commands in the Linux system, like for example ls or cd as well. Like you can
yeah,
run the dash dash help to view the manual for those ones as well.
yeah. Um, but okay, so the way this works is we give Python, so the program that's running the code, the name of the Python file, and it should be Python 3, yeah, ngrams3 count.py, and then we give a path to the data we're analyzing, which would be dot dot, which means go up to the parent directory, and then to the data directory, and then to the zip file. So this code will automatically decompress the zip file and find the text files inside of it without us needing to decompress it ourselves, which is a nice feature. And this, what we're about to see, is really significant here. So notice that we can run the same code on different data files without modifying the code. This is a command line interface that's been added to this code. So when something's really small, maybe it's not important, but it really is convenient if you start adding these to your own code. It can let you be a lot more flexible.
Yeah, often
Okay.
like these are called arguments for the script. So this is called like, for example, the ngrams count is an argument to the Python command, and then the data Gutenberg thing, yeah, is an argument for the ngrams. So
Mhm.
the
Yeah.
by giving these arguments, we can change what data we want to uh, analyze, and we can also give other things as well. So this is often called scripting, and we
Yeah.
Code Refinery has a great course, or Code Refinery will have in its course very useful like teaching on how do you start scripting your own code into this sort of format, because like
Mhm.
if everybody follows the format, everybody gets stuff done faster. So
Mhm.
I highly recommend joining that course that's coming in the spring to learn more
Okay.
about this.
Yeah.
So let's try it out,
So
right?
yeah, let's push enter. So it's telling us a little bit about what it's doing. Um, so where this is running right now is on the login node. So yes, it's on the Triton cluster, but it's not really using the Triton resources. It's using just one place that everyone has access to. So this is okay because it only lasted 20 seconds and we're just verifying things are working, but sometimes people log in and run all their code here, and then they're not actually using the resources and are slowing things down for everyone. But yeah, let's see, what does the output say? What do we get from this?
So it seems that we got the ngrams that are size 1, so basically like letter frequencies in this case.
Mhm. Yeah,
So there's a lot of
so
spaces there.
space is the most common character, and then E and T and A. Yeah, I mean, that looks about what I'd expect from English character frequencies. There's different Unicode characters in there, so there's some other languages. But yeah, so it worked. So we've transferred our data, we've gotten the code working barely, and now we're ready for the next parts. Did we get all our explanations? We explained help, the actions.
Hmm.
Um,
So should we now modify the what we previously run so that we can run it in the queue? So what sort of
yeah,
modifications do we need to do for the
yeah,
command line
yeah. So
call in order to run it in the queue?
yeah. So I guess whenever I run something in the queue, so in the queue basically means we prepare our order, our request for computing. It gets added to a queue with all the other requests on there, and then gets run on some cluster node somewhere. And then those results will come back to us. So when we say running in the queue, that's what we mean. So in
Hmm.
practice, since we haven't been running much on the cluster lately, we will have first priority. So the queue sort of looks at how much people have run, and the people that have run less have higher priority, and so on. So it won't look like a queue, but in reality, there is one under the hood here. And to test things out, I'll usually do things interactively first. So that means I we run it in the queue, but we see the outputs right here. So for this, we add the command srun to the start of our command. So srun means like slurm run. So slurm's requesting resources, and then we'll run it right away. We add this dash dash pty option, which basically means make it interactive. So it will show the output as soon as it's created and not buffer it up. Do we need to request some resources here? Like how much resources? So I see there's the
Yeah,
time.
so all of the jobs that we are requesting from the queue, they need to have they need to have some resource specifications of like how much does this job need, so that the queue manager can fit them to a correct place in the among the resources and among the other jobs. So the first ones we usually want to do is time, and we know that it doesn't take long time. So I will just say 10 minutes over here.
Mhm.
Uh,
Yeah,
but
seems reasonable.
it,
And some memory amount. So we know from our, actually we can look from here. So in the previous code, it says max RSS, which means resident set size or state size. Anyway, it basically is how much memory it's used. So it says it's using 44 megabytes, so we can give it 500. Um,
yeah,
I mean, anything less
just
than
to
a
be in
gigabyte
case.
is
Mm,
like so small that it basically doesn't matter. So,
yeah. Usually, when
okay.
you're requesting these, you want them to match what your code is running, and in this case, like it's
Mhm,
close to the ballpark. We just give it a bit of a leeway, like it has a bit more
mhm,
time headroom, and then a bit more
yeah,
memory headroom for the
yeah.
code.
Okay.
So
Should we
should
try
we
to
try
run
it
this, or
out?
do we need more options? Okay, yeah, let's
By
go.
default, yeah, by default the job gets one CPU, so I think this is good enough. So I don't think we need anything else. So what
Okay,
do we see
yeah.
now on the output here?
Yes, there's this new thing, Slurm job ID, something queued and waiting for resources, allocated resources. So we see some sign that it's got added to the queue and is waiting for resources, and it got those resources. And I guess we're waiting the same 20 seconds for it to run. And yeah, there we go. It looks pretty similar, maybe a little bit slower, but well, it had to start up and read the data and stuff like that. This is good enough.
Hmm. Should
Yeah,
we
what should...
should we create a batch script out of this and then have a small break after that?
Yeah, sure. Okay, so now we've run things the most basic way right now. This is interactive, but with this, we can only run a few things at a time because our own brain has to be sitting here and waiting for the output to come out. But instead, what we can do is we can basically write up our orders and then submit it to the queue, let it go process overnight or however long, and come back later. So it's like walking to a restaurant and saying, I would like this takeaway order. And then instead of sitting there and watching them cook, they prepare it while you go walk around and do some other shopping or whatever, and then you come back and your order's ready. So for that, we go to the realm of editing files. So Nano is a simple command line based text editor. And there's an output file here called run ngrams.sh. And this will be what we call our batch script that has the order of stuff.
Yeah,
And in the
the
file,
name.sh means that it's a shell script. So usually the ending means what the script type is. And in this
yeah,
case, it's a shell script. So some instructions for the command, like basically terminal commands that should be executed whenever the job is running in the queue or
yeah,
on the actual machine.
yeah. So the other things Simo are writing here are basically the magic words to make the shell script work. So we know this by heart because we've been doing this so many years, but in practice, what you'll do is you'll find one of the examples and grab it and then copy and paste it. So don't worry. The first line says this is a shell script that should be run by bash. The second and third lines, this hash sbatch. The hash is a comment character. Um, and then dash dash time. These are like the same options we gave to Slurm. So Slurm automatically finds
Yeah.
them
So
from
so
these comments.
yeah, well, when we give these to the queue system will look through the script and it will search for these kinds of statements, and then it will determine
Mm-hmm.
what are the resources needed for the job.
Yeah.
And then when we submitted it, it will go to the queue, and then once the job is in the queue, once it gets a suitable compute resource, it will use this executable, in this case the terminal itself, to run all of these commands. So it will basically type for us in that computer when
Mm-hmm.
once it gets the resources needed. And
Yeah.
over here, I've added a few extra options to the call that we previously had. So maybe Richard, you can explain what these options mean.
Yeah. So in the code, if you looked at the help text, the dash n2 means now we're taking 2 grams. So instead of simple character frequencies, we'll have all the frequencies of pairs of characters. And dash o is output file. So it will be saving the output to ngrams dash 2 dot out. And then we
So
have the
let
same data file as before. So we can save and exit. So in Nano, it's Control X and then Y and
Y and
enter or
enter
something
after.
like that
Yeah.
to save. So can you run
And now we
ls?
have a
And let's
yeah.
see. Yeah. So
Now we
we
have a new
see we
script
have
here.
a new script run ngrams. And to submit this to the queue, we use the command sbatch, which means like slurm batch submission. And
Yeah.
once
Don't
Timo pushes this, it will be added to a queue, and it will probably run very fast. So CMO will very quickly try to
Yeah.
run the command slurm queue to see it's still running. Okay.
Yeah.
Yes. So there we saw the submitted batch job stuff. So the command slurm queue says there's job 58196061 running. Yeah, it says state equals running on node PE71.
Yeah. So with when we submitted it with the sbatch, we can see the queue status with the Slurm queue, and because like this is such a small job, it will basically go immediately to the queue. So, but with the Slurm queue, we can check how long does it take for our job to get running, and once it runs, what do we get? I type ALS now in the in this folder here. So
yeah, so it's done, and we see two new files. One is slurm-some-number.out, and that's the output from the script itself.
yes,
The other
so
one
we
is
can use
ngrams2, and that's the output of the
yeah.
code. And let's look at it.
So we can use this program called less, which is a pager to view the file. So just to view the contents of the file. So I will first view the Slurm output.
Yeah. So this is just this management stuff. We see it took 25 seconds, about the same amount of memory. Yeah, okay, looks good.
Yeah. And I can quit I'm still in the program less because it's an interactive program. I can use the letter Q to quit here. So now I'm back in the command line. So what the Slurm did for us, that even though we set to the program that, hey, put the output into this file, and it wrote the output to that file, we also told, like, Slurm also will capture whatever output the code would say to the terminal, basically. Like if we would run the code and we would see some output in the terminal, Slurm will always capture that, and it will provide it into this output file. We can change the output file name by giving an sbatch command, but that's a different thing. But it will always capture that, so you can always like see what is the output. So it's like, compared to the interactive running, it's not that different. We just like we tell it what to run, and we can always see the output. So
yeah.
And let's look at the ngrams output now.
Okay, this looks more interesting. E space T space T H E TH. So the is definitely the most common word there. Who would have thought?
And an empty space and an A article is quite, or N article is quite common as well.
Yeah. Okay. So yeah, there we ran our batch script. Anything else before we go to the break? Should we look at the timings?
Yes.
And the history.
So when we have run something in the queue, we can run Slurm history. So the Slurm is this command that has various features that you can use. It's like a easier way of accessing the Slurm output, and we can see like let's say Slurm history from 1 hour. I have run some other jobs previously, so they might be here as well.
Yeah.
We can see. Actually, we don't see any other jobs. So we see here
there's
that
just the two.
Yeah, so here's the interactive one, and here's the non-interactive one, the batch job run script.
Yeah, and we see the requested memory, the amount of memory it thinks it used, CPU time. Can we see the efficiency of the job? So how much processor and memory it actually used? So if we copy this job ID,
each job gets a job ID that specifies, like, well, it's unique identifier that you can then look stuff up with, and we can use this command called sf to check the efficiency of a job. So if we run sf and then the job ID, we will see like what was the efficiency, and we can notice here, for example, that the CPU efficiency was very good, 100%, but the memory efficiency not so much. But
Yeah.
this was such a small job that it probably didn't even capture that, because these are sampled values that are sampled every so often, and the job is
Mm-hmm.
so fast that it probably didn't even capture them
Yeah.
correctly.
Okay, great. So should we quickly look at the notes and then go to a break?
Yes.
I'm switching to the notes on my screen. So there's some good questions here. Most of them have been answered, or we can talk later. Um, Someone asked about the priority. So how is the priority calculated? Um, is this something we should answer now, or because it's
So
actually
I can,
pretty complicated, but maybe Simo
yeah,
has a quick
yeah.
explanation.
Yeah, so the priority is basically calculated based on your past history, and the sizes of your jobs that you uh, previously submitted. And the size of the job is calculated based on the number of CPUs you have requested, or the number of memory you have requested, or the GPU resources you have requested. So everything has basically like a price, and
Mhm.
those the size of the job, so memory request, CPU request, GPU request, times the time gives like a, I'm gonna say it like a block, like volume of the job basically in the cluster. So that is used to calculate like your usage, and your priority is basically like it has a half life of, like, for every job it just has a
Mhm.
half life of
Mhm.
2 weeks where like the priority goes down. So basically it's just like tries to make it so
Mhm.
that everybody has a fair share of the resources. So if somebody runs a lot of big jobs, they get less of them in the future so that other people have the chance to do it. So the best thing usually is to just run what you want to do and keep the resource requests close to the what your jobs need. And there was a question of how do you choose these ones. So usually the good answer is to measure what your job needs and check with, for example, SF, what your job needs. There's a full documentation in the SciComp documentation on how do you measure these. But usually, usually you want to um, measure what your job actually uses so that you can choose the appropriate resources. So you run an example job and then you check how much it used, and then you lower the resources closer to the actual resource needs, giving it some leeway so that, like, if there's a memory spike or something like that, it doesn't um, it doesn't go over the memory limit, or like if you give it a bit more leeway in the time department so that you know that it finishes in time.
Yeah. Um, the other question I might answer now, how do you estimate the memory and time needed for a task? And this is a really good one. And basically, I guess I'd say experience and knowing the problem. I mean, there's no one magic answer here, other than just run it and see what it actually uses. So for example, if it runs on my own computer, I know it won't need more memory than exists on my computer, and start with a few CPUs. So um, usually I'll start and I'll request more memory than it needs and see how much it uses, and then decrease to the amount that's used. If you don't request enough, you'll get an out of memory error, and then you know you need more. And for CPUs, we'll talk about how to scale up the number of CPUs you use to see what's the proper amount there.
I highly recommend looking at the guide posted also to the notes on like what sort of measuring sticks you can use to measure the program size. Also, there was a
Yeah.
question of is time requested or time used the one that is calculated using the priority, and it's quite kind of both, because when the job is in the queue, like your estimate like of how much time it will use is used to calculate like how big the job is, how like if you say that I want the whole cluster for 1 month, the job is huge and you won't get it ever because it's such a big job. Like it's impossible to get that much resources at one time. And if you then the perceived time usage is like, or the requested time usage is used to calculate the priority. But once the job has finished, the time usage that it actually took is the one that is used to calculate your like past priority. But in any case, it's best to just try to match the request as close to the actual usage as possible, and to do some simple measurements to get to the right ballpark. So if you know that the job finishes on your laptop in 15 minutes or maybe an hour, you don't need to request a full day's time in the cluster, because like it's way overboard because it takes an hour on your laptop, so might as well put an hour in the cluster as well.
Yeah.
But maybe we should go to a break.
Yeah. So I guess we come back at 16 minutes past the hour in whatever time zone you're in, unless you're in a weird country, which is fine. Yeah, you can keep answering or asking questions. We'll keep answering, and when we come back, it's parallel stuff. So see you later. Bye. Hello, welcome back from the break. So looking through the notes, I don't see any new questions we haven't answered, so I guess let's continue with our task. But maybe first, we're gonna do parallel now. So what does that mean, parallel? And how are we approaching this?
Yeah, so this is I would say quite like it's way too complex of a thing to like to have everything said in this small session. But it basically means like using more than one processor. And there are multiple ways we can do this. And the most important one, I would say, that we are going to be focusing on this session is this kind of embarrassingly parallel, where we just run the same thing with different inputs multiple times. So we just basically we would start the same program multiple times and that is the easiest way. But there's all other paradigms as well. There's multiprocessing, there's message passing interface parallelism, MPR parallelism. But it basically means that we use more than one processor. So you know that your laptop probably has 8 to maybe 4 to 8 CPUs already.
Yeah. While I was making the kitchen videos, I had to very carefully research what is parallelism. And I think the answer I got is that there's more than one point of execution at the same time. So we have multiple processors. One processor is executing our analysis on one book, and another processor is on a different book. And this is what I guess we'd call data parallelism. And in particular, we will use first array jobs, which is embarrassingly parallel. So basically, instead of running one program that does multiple things, we run 10 copies of the same program. And then these 10 different copies will all process 10 different books within the 100 books we have. And they'll all write out separate files, which we can then combine later and hopefully see the same output.
Yes. So these kind of problems arise all the time. So if you have different data sets you want to process, if you have different parameters you want to process, you want to do different options, different random number seeds or whatever, like there's multiple different ways that you encounter the situation where you do the same thing but with a small difference. And in these cases, the embarrassingly parallel parallelization is your friend. And even though it's called embarrassingly parallel, it just means that it's easy to parallelize. And in this case, like Richard said, the book analysis is very easy to parallelize. So maybe we should look into it.
Yeah, so I'm switching to your screen. There we are. So we're back where we were. So we already have a working batch script, the run ngrams. So I guess we can make a copy of this with the cp command and call it run ngrams array.sh.
Oops. First argument first.
Ah,
So first, what are we
yeah,
copying, and then the other one. Yeah, my mistake.
yeah.
No. Yeah.
Okay. And now we can open the new file, the array running file. So we need to tell this program that it should run as an array. So we add a new Slurm option here. So the sbatch comment, and now we give array equals 0 to 9. And that means the same file will run 10 times, and each time there'll be one different variable inside. And that variable would be set to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And how do we use that variable? So the program count.py has built-in support for this. So there's this extra argument we can add in --step equals 10. So step means it will run every 10th book, and start will be tell it what book to start on. And here we use the magic word slurm array task ID. And this is something you would just look up from the array examples. Like there's no way you would know this by yourself automatically. So yeah, so now 10 times they run on 10 different books. So the first one runs book 0, 10, 20, the next one book 1, 11, 21, and so on. Do we need to have them save the output to different file names?
Yes. So I added here to the output also the task ID, because otherwise they would they
We
would all
can't
try
see
to
that.
write in
Can
the same.
you make it
Oh
narrower?
yeah, yeah,
It's
that's true. Yeah,
scrolled
my
off.
bad. Yes.
Okay, yeah.
So unfortunately this wraps this code, but
Oh,
yeah, on the
that's
output
a bit,
one, I added
yeah.
this this Slurm array task ID
hmm
there as well. So because
Yeah.
like otherwise all of them would write to the same file. So when we
hmm
are submitting this job with the array structure, we are telling the queue that, hey, I want actually 10 of these. I want 10 of these, and just give me a different number for each one of them. And based on
Yeah.
what number we're getting, we do something. And there's various things you can do to map this number to parameters or whatever. There's multiple examples in the documentation, but this is like a simple example where we can straight up use the number over here. So should we try it
Yeah.
out?
Yeah. Okay. So now we submit it with sbatch again.
And I'll try to be again fast to get the
Mhm.
queue status.
Yeah. So
Yeah.
queue. Okay. So we see here now there's 10 different things running. 0, 1, 2, 3, 9. We see there's the underscore and number, which is the different array tasks. They're all running. On the last column, we see under node list, many of them are running on a node named PE32, but there's a few that are running on other ones. So basically, we've managed to run on different nodes here.
Yeah. And it's important to note here that all of these jobs are completely independent of each other. So they don't
Mhm.
understand, like if you have a program that needs to somehow communicate among the different things, it's not an array job. You need other parallelisms to use, like to run that sort of program. Of course, you can then run that with an array job if you want to like run multiple of those kinds of programs. But here, all of the programs that are running, all of the scripts that are running are completely independent of each other. So they do independent stuff independently, and then they uh, give the output at the end. Should we look at the outputs?
Yeah. So now we see there's output ngrams to array 0, 1, 2. You want to look at one of these and see.
Yes, let's take, for example, these.
Yeah, I mean, it looks like the normal thing, but about 1/10 as much data there.
And if we look
So
at any
there's
of
all,
the outputs here, we can notice that,
yeah,
well, it looks similar as well, but again, like the number of ngrams is 1/10 of the um, of the overall amount.
yeah. Okay. So there's also a script included in the HPC examples that will combine all the output, because presumably we don't want 10 separate output files, but we want one. So it's, I think, called combine counts.py. Yeah. So it takes a series of input arguments, which is um, the inputs. So we can use this glob syntax. So the asterisk means fill anything that um, matches this pattern. And we can use the -o argument to write it out to another place.
So this is often called like a map reduce kind of a thing, where you do something over
Yeah,
multiple things. You do this mapping, and then you reduce the information together. So this is
yeah,
quite common in like data heavy stuff. You want to do
yeah,
stuff independently and then combine the outputs together.
yeah. So now we see the new output file. Do you think it's the same as the original one? So it
Well,
should be sorted by amount. Should we look at the first 10 lines and see if they're the same?
yeah, let's do that. So
So
let's look
there's
at the
this little
original one
program.
first.
Yeah. What does the program head do?
So it prints out the first lines of a file. It by default it prints X number. I don't remember, but we can give it a number what we want. But you can look at the start of the file, like if you want to check what the data looks like or something.
Yeah,
So if you
so
look at the
that's
first 10
the
lines there,
original and combined. So the moment of truth, is it exactly the same? And those counts look pretty much the same to me.
hmm.
Yeah, so it worked.
Yeah, so we didn't have to do any modifications to the code itself. Like it was the same exact code that we run. Well, of course, the combination we had to there had to be some sort of way of combining the results after the fact.
Yeah.
But there wasn't any like major modifications to the code itself. Like we could run it separately. Of course, like
Right,
yeah, like
yeah,
you need to have some way of mapping the Slurm array task ID to the task what you want the code to
yeah.
do. But once you have figured that out, it's usually plain like smooth sailing to get easy way of getting lots of parallelism in the cluster. And this is very
Yeah,
good for like jobs that you need to do something
yeah,
a lot of times.
yeah. And this is your own brain power that you'll need to spend to figure out how to distribute things and split it up like this. And this is what it means to be a scientific computing person. But okay, there's other options. So there's also a mode of this which tries to use multiple processors within the same program, something called multiprocessing, which is a Python module. And would you like to give that a quick try?
Yeah, let's try it out. So
Yeah.
if we first try running the previous single uh, core version. Like let's try out that and let's just verify what we had. So
Okay.
I copied
Yeah.
uh
Okay.
from
From the earlier
history.
one.
Like yeah,
Yeah.
so here I'm running the code. The only change here is that this time we are checking for words, like word
Mm-hmm.
um like instead of letters we're checking for words for the ngrams.
Yeah.
So
Okay.
it will be a bit it takes a bit more for the job to run.
Yeah.
So
Okay. and we see it used more memory, 500 megabytes now, about the
Yeah.
same amount of time. Okay, so we've done it with one processor.
With a code that
Let's
isn't written to use multiprocessing. But if
right.
we are starting to use like multiprocessing, the first things you must check is that does your code support it? Like is your code written so that it understands multiprocessing? In this case, this
Mhm.
program isn't, but Richard has written a version that does support multiprocessing, right? So and this is
Yes.
called count multi.
Yeah. So now it basically works the same, except we will tell it it should use um, more processors. So first we have to request the extra processor from Slurm.
Yeah.
So
So first, yeah,
yeah. So within the srun areas of the arguments, we'll request CPUs per task equals how many? 4?
let's say 4. Yeah.
Yeah, let's
Let's
request
put a
4.
bit more memory because there's going to be overhead because all of the processors are going to be uh, needing memory. So, but this is like we have now requested. So in the Slurm, so
Mhm.
if you look at this block of text before the Python
Uh,
command, so where we have the srun and we tell the Slurm requests, we have now used CPUs per task equals 4 to
mhm.
request more CPUs.
Yeah.
You don't have to worry about the task. It's a different thing for MPI stuff. But CPUs per task basically asks for 4 CPUs. But the code yet doesn't. Software updates, nice. The code yet doesn't like know how to use those processors
Mhm.
unless we tell it that okay, you should use 4 processors.
Yeah.
So different programs have different ways, and it depends on the program. But
Yeah.
usually, if you have multi-process like code that is can utilize multiple processors, there's a way of telling it how many processors it should use. And in this case, I think it's threads. Right, Richard?
Yeah. Okay. So I think now this has everything it needs. So we're saving to the
Yeah,
same output file. That's fine. Should we try running it
yeah.
and see what happens?
Yeah, let's put threads for let's put a different
Yeah.
file. Let's see if the head is like the output is the
Okay.
same.
So it's running. It says it's using 4 processes. And so while we're waiting here, do you think this will be faster or slower?
Well, it's probably going to be a bit faster, but not that much because
Okay.
the um program probably cannot there's multiple things that can happen there, but like
Yeah.
this kind of a example test case probably
Yeah.
won't parallelize that well because there's lots of
Yeah.
overhead and that sort of stuff.
Yeah.
So
So this is really interesting. So it ran. So let's look at these numbers carefully. So first there's the wall time. So wall time means like the clock on the wall, so the real time that's passed. So we've requested 4 times as many resources, and it's run, what, 20, 25% faster, something like that.
yeah,
So
something like that.
basically, most of our extra resources appear to have been wasted. Ideally, it would run in 1/4 of the time, but really it ran in 3/4 of the time or 4/5 of the time, something
Mm.
like that. So this code really didn't work well with multiprocessing. Let's look at user time. So user time, and this is the amount of time that the processors actually spent doing work, it went up from 21 seconds to 29 seconds. So this is okay. Like you'd expect it to run a little bit slower. It has to spend more time communicating between the different parts. But yeah, combining this with the wall time not really going down, it shows that our parallelization really hasn't worked. And that
And
goes to a
let's
question which is in the notes. Should we do the changes? Like, should someone do the changes to make their code support multiprocessing? So it really depends if it, like what the code is. Is it going to be efficient? Simo's running SF
Yeah.
here.
Yeah, let's run quickly like SF and the job IDs of the jobs. So if we take the job IDs from the output over here and look at them, we can see that the first one had a CPU efficiency of like 90%, and the second one had a CPU efficiency of 40%. And like Rich said, like the parallelism, it really it depends on the case that you're running. If you're running like a physics code or something, the parallelism might be needed. Otherwise, you might like not get the results in a reasonable time. If you're running like a data hungry process that tries to do like run, for example, in here we are trying to go through multiple files. There might be a lot of overhead with the file reading and writing and that sort of stuff that doesn't really help. And in actuality, running the array job would be faster. So sometimes running serial, but more of them, is faster than running something parallel, because like there's these overheads that are needed to make certain that the communications work and that sort of stuff. So multiprocessing really depends on the case, and if it's like low level codes, it's usually better. If it's like this kind of like run through something like data, it doesn't necessarily help, but it's usually best to test. It's usually best to test and see like how does it work. But usually like if you have an existing code trying to get the results done, like there's a question of, do you want the results done or do you want them to be done faster? And there's like, if you want them to be done faster, you might benefit from multiprocessing because the wall time goes down, the time it takes to run them. But if you want the results done, let's say you will need to run 1,000 simulations or something, it doesn't necessarily make sense to parallelize them because there's 1,000 of them, and the overhead starts to accumulate. Instead, it might be just better to run 1,000 individual simulations and not parallelize them at all, because that way you reduce the overhead time and you just get them done. So array jobs are quite often the fastest way of getting bulk stuff done. But if you want something like you are waiting there in the queue, waiting for the results to come by, then the multiprocessing might make it faster to do that specific simulation. But it's like a question of, do you really want to go through the hassle? If your code already supports it, it might be good to check if the code has support for multiprocessing and then test it out whether the multiprocessing version is faster.
Yeah. As an example, when I was making these codes, I maybe spent 15 or 30 minutes getting a first version of the single core code working. It was pretty fast. And then I spent many hours working on the multiprocessing version. I could make something that initially worked quickly, but then understanding why it was slow and trying to make it slightly better took a long time. So this might also be what you'll experience for your own stuff. But should we talk about some of the speed considerations and why it's so slow? There's a good question about why is the multiprocessing slower? Or is there something else to talk about first?
Yeah, I would say that like in this case, there's few considerations. So first off, it needs to load the data for all of those different multiple processes. So it needs to open the file 4 times. Like each one of them needs to load the file in order to get the data in. So there's like data slowing down. Then it needs
and
to,
I can say, from my experience in making this, the program is a little bit faster when it reads the data directly from the zip file compared to uncompressing the zip file and running it on all the files separately, opening them independently. It really depends on the format the data is stored in and all that. I could have repackaged it into a format that optimized for reading and it would be even faster. But this is a real thing that you can experience with this example if you want to give it a try.
And also, like if you think about the word counts, it's calculating the word counts. It has to, like each process that is analyzing different file, it needs to store those words into like the memory, into the counts, like how many counts has this word appeared, or had this ngram has appeared. So each one of them has to house its own copy of this kind of like
Mhm.
word dictionary, and that of course means that there's 4 times the memory usage. We see also the memory usage grow because of the extra CPUs. So there's like these overheads that happen when the individual processes have to like do the same stuff that the one process would do as well, and then that makes it slower. And
Yeah.
these kinds of considerations happen. Like in some problems, there might be a situation where like you get benefit, but you only get benefit once you get over the overhead. Like basically, like let's say we would have 1,000 books or 10,000 books, then like
Mhm.
the
Mhm.
overhead is smaller because now we can reuse the same processes most likely, and do the
Yeah.
calculation like the word counts. But it depends on many factors, and and
Yeah.
and yeah, like there's no one simple reason uh,
Yeah.
why it
So
might be faster or slower.
yeah, there is the point, this moving data between processes in multiprocessing. That's a big thing here. So Python multiprocessing isn't actually shared memory. There's actual different processes. So it has to use inter-process communication to share the data. And in practice, the way the program stores the data is relatively inefficient. So it apparently takes a long time to do this sharing of the computed ngrams between things. So
But again,
yeah,
the question, when you're encountering these sort of
yeah,
situations, it's usually a good idea to like measure your program, profile your program, and ask us maybe like, is it worth
mm-hmm,
worth the effort
yeah,
of trying to parallelize something before you start just putting
yeah,
more hardware to the problem? Because sometimes
mm-hmm,
the correct solution might be to look at the problem from a different point of view instead of like, okay, like looking at it from the point of view of, okay, what do I actually want to accomplish, instead of like, okay,
mm-hmm,
I just want to use a fancy word for doing that.
yeah. So there's one final thing I'd like to say, and that is the input and output, like someone mentioned there. So I noticed when saving this, you notice it's a plain text output format, which is good for most purposes, but it has to create every line individually. And every line has a JSON serialization where it puts the words and letters into the brackets and stuff like that. And I found that in practice, that's slow. It can spend a lot of the time just writing this output. And when you're trying to use the data, spend a lot of time reading the data in, especially when the number of books starts getting larger. So basically, the processor itself for doing this kind of analysis is so fast that the format the data is stored in becomes the bottleneck here. And since it has to write it all once and it's not writing it in parallel, it's writing it in serial. So that becomes a bottleneck and slows things down. So all of these considerations. So the data thing, especially when you're doing things like machine learning training, GPUs and so on are so fast that oftentimes the speed of getting data to the GPU is the bottleneck here. If you don't use the good data loaders that operate in other threads, if your data is not stored in a preprocessed format, you end up taking more time with that. And that's a really nice thing about this example because we can actually see the slowdowns because of the data, I/O, and so on.
Yeah,
Okay.
it's usually good idea to remember that like when it comes to computers, like let's say accessing like a memory register is
Mm,
few seconds. Like let's say the scale is something like it's actually like nanoseconds, but like let's say it would be like few seconds. Then like and accessing the memory, the RAM memory would be like few hours or something, and
mhm,
then accessing a hard drive or a network drive or whatever that would be like years.
Mm-hmm.
So it's like the
Yeah,
scales are, because we're talking about milliseconds at that point, like,
yeah,
so we are like the scales are wacky when it comes to computing. So it's usually good idea to measure stuff when you're doing stuff, yeah, and like think about,
yeah.
okay, like is it worth to create more complex code just to
Mm-hmm.
get basically nothing out of the exercise. But
Right,
of course,
yeah.
sometimes you have to do it. You have to test it out to see if it happens. But this, it's good to remember that like normal everyday life experiences don't necessarily translate one-to-one to
Mm-hmm.
computing environments. Like you might encounter that, like it's suddenly um,
Yeah,
yeah, some suddenly something behaves differently. But also I would say that
yeah.
existing codes, so like nowadays, a lot of existing codes, scientific codes especially, are written
Mm-hmm.
to support multiprocessing straight out of the box. So multiprocessing is not bad if it's written correctly, and in many cases,
Mm-hmm.
like if you're using R or NumPy um, or any machine learning framework or whatever, they support multiprocessing by default. So it's a good idea to check the documentation of your specific case. Like, does it
Mm-hmm.
support multiple processes? And if it does, then
Yeah,
utilize them if they make your problem go faster.
yeah. Do you want to show how we can use on-demand to look at the outputs of the things to wrap up?
Yes. So I have here
So,
the folder so I can see it over here. But if I want to look at it in a more graphical way, uh, I could also go to the start place on the on-demand and start, let's say, right on desktop. So let's start one. So this is basically like a virtual desktop that is running on one of the compute nodes in the cluster. So it's a pretty bare bones experience, but it's very good if you want to, let's say, view a plot or something, and you don't want to transfer stuff or to and fro from Triton.
mhm.
So it's now running, and I can launch the desktop over here.
Oh,
So you notice that
cool.
I
So,
now have a place
and
here.
this is running on the Triton file system on Triton. So can we go and access Scratch,
Yeah,
for example?
yeah,
However, we navigate to it with the browser.
yeah. I'm
So
typing Control
Scratch,
L to get this a Scratch work. My username teaching
teaching.
Kickstart. Let's go here. Let's
Yeah, okay.
go to, and I could even use the editor here to edit it, but there's alternative editors that you can use as well. But let's say I want to
Right,
view
yeah.
one of these outputs, I can just open it up and with an editor
Yeah,
and see it
it's
up.
there.
So so if you
Okay.
want to view a plot or something, you can, or you want to do some simple edits, this is also a nice way of
Yeah,
doing some interactive usage.
yeah. Okay. Maybe I'll switch back to the notes here and
Yep.
we can see what unanswered questions there are. The other instructors can join us for the outro. Um, but yeah, this was
Yes.
um a general yes, okay. So in the notes now there's a feedback for the morning part. So you can answer the poll here, tell us what you think. So too fast, too slow, whatever, a good thing about today, something to improve, any other feedback, and so on. In the meantime, what's our plan? So we have a lunch break coming up, and then we'll go to Zoom. And in Zoom, we will be able to answer more questions and basically do all of these different examples and exercises together. So, like you have the time that you can work on it yourself, ask more questions, we can look at your individual problems, and so on. There'll be different breakout rooms there focused on different topics. Um, yeah. Do you want to give the outro and then we can look at the notes questions? and keep answering
Yes.
questions until it's the end. Okay. Are you?
If you
Shall I switch to your
switch
screen?
to my screen, yeah, exactly.
Okay.
Yes. So
Simo, could you stop sharing? Because yeah.
Yes.
I'm still sharing.
Okay. Yeah. No.
Should I
But
restart my sharing?